Okay, this is a walkthrough of what we did in class on writing electron configurations. I'm going to give you a little bit of background about the periodic table and how it relates to the addresses where we can find electrons. Alright, so the first thing you need to understand is a little bit of background about atomic theory and quantum mechanics. Originally, when we discussed locations of electrons, we thought of electrons as traveling in what we called orbits. In other words, if this is the nucleus and this was an orbit, we could predict at any given time the location and the direction and even the speed of that electron. And that would be sort of like how we know that, say, Earth is orbiting around the sun at a particular speed at any certain point of the year on any day. We know in relation to the sun where the Earth is, how fast it's going, and the direction that it's going. Alright, so what we discovered was that orbits really didn't work. It didn't explain the behavior of electrons. And so two different scientists really governed what we would today believe the quantum mechanical model of where we find electrons. So one was Heisenberg, and Heisenberg came up with what's called the Heisenberg uncertainty principle. And the Heisenberg uncertainty principle basically says that it is not possible to know the location and the direction of an electron at the same time. That if you simply try to measure one, you actually will cause the other to change. And so we can't really know the orbit of an electron. We can't know its exact location and direction, speed, and all of that. What we can know is the probability of where it would likely be found. And that brings us to Schrödinger, who came up with an equation. And his equation came up with a set of variables that would explain all the possible addresses of where we could find electrons in an atom. It was a mathematical function problem, and then the function had several solutions. And those solutions represent all the possible locations that electrons can be found. Alright, so based on Schrödinger's equation, there were actually four variables. One variable is the energy that an orbital contains, and we call this the principal quantum number n. If you think about this in terms of what you already know about atoms, if this was our nucleus, you may have learned that electrons are found in energy levels or shells, and that's what n represents. So level n equals 1 is the one closest to the nucleus, and then n equals 2, and n equals 3, and these are basically what you've probably heard before are the energy levels. The second variable is the orbital shape. So we have the energy level of an electron, we have the shape of the orbital or the area where the electron is located, the orientation, and then finally the spin. Alright, so these are probably not going to make, particularly shape and orientation, are not going to make sense just yet, but they will. Let me talk really quick about spin. So here's the idea. In one particular orbital, think of an orbital as like a bedroom in an apartment, you can only have a maximum of 2 electrons. And those 2 electrons don't want to be next to each other, so they spin in opposite directions. So it's sort of like 2 people sharing a bedroom, and they want to be on opposite sides of the bed. And so this is showing an orbital, and we represent the electrons with little arrows, and this would represent an orbital showing 2 electrons with opposite spins. Okay, so we said that there's the principal quantum number, n, and this is sort of like the shell, or if we're going to go with the apartment analogy, this would be like the floor. So you've got an apartment, and it's got the first floor, and that's going to be level n equals 1, and then we're going to have level n equals 2 and level n equals 3. And it turns out that based on Schrödinger's equation, there's a certain number of electrons that can live on each floor, and it changes floor by floor. The formula to calculate this is 2n squared. In other words, on the first floor, 1 squared is 1 times 2 is 2. So exactly 2 electrons can live on the first floor. On the second floor, 2 squared is 4 times 2 is 8. 8 electrons can live on the second floor. Third floor, 3 times 3 is 9, times 2 is 18, So 18 electrons can live on the 3rd floor, and so on. And so this tells us the maximum number of electrons that could be found in any particular quantum level. Now, it also turns out that on each floor, the orbitals can have different shapes. So the first shape is called S, and it's actually a sphere shape. On the 1st floor, there is an S orbital, and it's called 1s because it's on the 1st floor. And on the 2nd floor, there's an S, and that's called 2s. And on the 3rd floor, there's 3s. So on each floor, there's a single S orbital. Starting with the 2nd floor, it turns out that there's an S orbital, but in addition, there's also a P orbital. The shape of the P is actually a dumbbell shape, and it represents 3 different ways that electrons can be traveling. So not only is P got a dumbbell shape, but it technically has there's 3 P orbitals, 3 different orientations that P can take. So think of a P as a 3-bedroom apartment. So on the 2nd floor, there is a 2P. On the 3rd floor, a 3rd floor P. On the 4th floor, 4P, etc. Starting on the 3rd floor, it turns out that there is another orbital shape called D. D is actually like a 5-bedroom apartment. And then F starts on the 4th floor, and it's a 7-bedroom apartment. So imagine that this is a very strange apartment building, and what you've got is this. On the 1st floor, you have just an S. On the 2nd floor, you have a 2S and a 2P, a 3-bedroom. On the 3rd floor, you have 3S, 3P, and also 3D, which is your 5-bedroom apartment. On the 4th floor, 4S, 4P, which is your 3-bedroom, 4D, which is your 5-bedroom, and additionally a 4F. And this would keep going. In theory, this would just keep going up and up and up. Each level would actually have one more apartment in it, and that would hold more bedrooms. Okay, so there are 3 rules about where electrons will be located in an atom. The first one is called the Aufbau principle, and it basically says that our electrons are going to fill the lowest energy levels first. Now, when we first start off, that's typically going to be the 1st floor of the apartment building. So in other words, if we were looking at hydrogen, which only has 1 electron, we would find that electron in hydrogen on the very 1st floor. Suppose instead we were talking about oxygen. Now, oxygen has 8 electrons. So if we were going to figure out where those electrons would be, the first 2 electrons would be on the 1st floor. On level 1, apartment S, 2 electrons. The second 2 electrons would be on the 2nd floor in 2s, and there's our other 2 electrons. That now accounts for 4 electrons. That means we need to account for 4 more. So in apartment 2p, we would find our other 4 electrons, 2p4. That gives us 4, 5, 6, 7, 8. And that would account for the 8 electrons in oxygen. Now, even though P holds 6 electrons, notice that since only 4 needed to be placed, oxygen in 2P would actually only hold 4 electrons, leaving some empty space. The second rule, Pauli exclusion principle, we already talked about. This is the one that says that electrons have to have opposite spins. So in the 1-bedroom apartment of S, you could only have 2 electrons. In P, which was a 3-bedroom apartment, you could actually have 6, 2 in each bedroom. Lastly, Hund's rule. Now this one goes back to what we just talked about with oxygen. Hund's rule says that if they're all living in the same apartment building, for example, in 2P, and there are 4 electrons, they will spread out equally. So if you only had 3, for example, in level 2P, they would be like this. You would not find them like this where they're next to each other. They won't share a room unless they have to. In oxygen, there's 4, so we would look at it like that. The first 3, and then the 4th one would go back and share. Okay, so there's certain rules to the order in which these floors fill. In other words, for example, if we were talking about hydrogen, hydrogen only has 1 electron. It's number 1 on the periodic table. If we wanted to choose the highest probability area of finding that electron, it would not be on the 7th floor, because there's rules about where electrons would be if we're talking about just a stable ground level atom that does not have any kind of a charge or anything like that. So the first rule is called the Aufbau principle. And the Aufbau principle basically says that the floors are going to be filled in order of lowest energy. Now the diagram I have here is actually showing the order from lowest energy to highest energy. In other words, if something has, let's say, 5 electrons, and we need to place those electrons, remember, going back for a second, that every S was a 1-bedroom apartment. It can hold 2 electrons. P was a 3-bedroom apartment. It can actually hold 6 electrons. The reason why it can hold 6 is because of another rule we have, which is called the Pauli exclusion principle. The Pauli exclusion principle says no more than 2 electrons can occupy a single orbital, and they spin in opposite directions. So P, being a 3-bedroom orbital, can hold, if we were to diagram it, 6 electrons, 2 in each of the bedrooms. That means D, which we said was sort of like a 5-bedroom apartment, would be able to hold 10 electrons, 2 in each of the bedrooms. And F has 7 bedrooms, so it can hold 14 electrons. Okay, so the electrons fill starting with the lowest energy. If something had 5 electrons, if we were going to place where those 5 electrons would be located, the first 2 electrons would be located in 1s. It can hold 2 electrons, so it would look like this, 1s2, telling me that on the first floor, the s orbital is full, it's got 2 electrons in it. The next 2 electrons would be found on the second floor in 2s. So we also would have on the second floor, in the 1-bedroom apartment, 2 electrons. The fifth electron, we said this had 5, this accounts for 4 of them. The 5th electron would therefore be found in 2p, and we'd write it like this. On the second floor, the p apartment has 1 electron in it. And this is what we would call the electron configuration for that particular element. So this diagram here shows the order that they fill. It would make sense, you would think, that they would just fill 1 floor at a time. The first floor would fill, then the second floor would fill, then the third floor would fill. But unfortunately, that's not the way it works. What we've discovered is it actually takes less energy. For example, we fill 1s, then 2s, then 2p, then 3s, then 3p. So far we're going in order by floor, but we've discovered that what really happens is that it takes less energy to fill 4s than to fill 3d. So atoms don't actually fill the whole third floor first. They actually go from 3p to 4s, then back to 3d, 4p, 5s, then 4d, 5p, 6s. In other words, if you follow the arrows after 6s, go to the next arrow, 4f fills next. So this is the actual order that we've discovered that the bedrooms fill for electrons. So if we want to know the addresses of all the electrons in any particular atom, we just start with the ground floor, use our Aufbau principle, lowest energy first, put only 2 electrons in any particular room, and we just keep going until we run out of electrons. So let's say we were going to do one that had, let's say, 14 electrons. If we were going to fill whatever element has 14 electrons, we would do this. We would know that the first 2 electrons would be found in 1s. The next 2 electrons would be found in 2s. The next 6 end up in 2p. So far, that's 10 electrons. We know that there's a total of 14. Where does this go after 2p? It goes to 3s. 2 electrons can go there. We're now up to 12. The last 2 electrons will therefore go in 3p, which can hold up to 6, but in this case is only going to have 2. So that's how we would write an electron configuration for that particular element. Now, we can also draw what we call the orbital diagram. An orbital diagram is sort of a physical representation of the same thing. It looks like this. Here's 1s, and this is physically showing the 2 electrons with opposite spins in 1s. The next thing we said filled was 2s, also has 1 bedroom, and it would look like this. 2p has 3 bedrooms, and it's filled. So 1, 2, 3, 4, 5, 6. 3s was next. It has 2 electrons. And finally, 3p. And when you draw 3p, it's really important we follow one last rule. And this is called Hund's rule. Hund's rule says, basically, that electrons don't want to be next to each other. So if you have, for example, a 3-bedroom apartment, these are all in the same apartment, same amount of energy, and you only have, like in this case, 2 electrons, the proper way to write it would be 1, 2. It would be incorrect to do it like this, because electrons want to be as far apart as possible within a single level. So we couldn't just take one of the S ones and move them up, but within a single apartment, if it's a 3-bedroom apartment, we're going to put our first 3 electrons into the 3 separate bedrooms. If it happened to have 4 electrons in P, we would go back and then start filling them in next to each other. And that's called Hund's rule. And you can see that physically when you're writing orbital diagrams, but you won't actually see it physically when you write out an electron configuration, because this doesn't actually show you a graphic representation of where the electrons are located. The periodic table is organized based on how these levels fill. For example, everything in the first column right here ends with S1. Everything in the second column ends with S2. This whole section ends in D1, D2, D3, all the way up to D10. In fact, this is actually called D block. Notice it's exactly 10 wide, which makes sense because D holds exactly 10 electrons. S was 2 wide because S actually holds exactly 2 electrons. This over here is called P block. It's 6 wide because P holds 6 electrons. And finally, this down here is F block, and since F holds 14, it's 14 wide. Everything in this one ends with F1. Everything here would end with 1, 2, 3, 4, 5, 6, 7, 8, so this would end with F8. This element right here must end with D3. This element here ends with P1, 2, 3, P4. Everything here, except for helium, ends with P6. So the periodic table is organized not only into blocks in which each thing in the same column has the same ending, but it's also organized in the exact order that the electrons fill. Here's what I mean. Remember our little order of filling? We had 1s, 1s2, then 2s1, 2s2. What comes next? 2p up to 2p6. Then 3s2. Then 3p6. Then 4s2. And if you remember, they didn't fill quite in order. After 4s2, it went back and filled 3d up to 10. Then 4p6. Then 5s2. Then 4d10. Then 5p6. In other words, the table's organized in the order that the electrons actually fill their shells. 3d doesn't come until after 4s. So let's practice writing an electron configuration. Suppose we were going to write the electron configuration for zinc. It's right here. It's number 30 in the table. Now, one thing you could do is you can remember what I just told you. If this is D block and everything here ends in D1 all the way up to D10, you pretty much already know zinc must end with D10. That must be the last thing that fills. But you can also do this. Here's our little way of remembering the order that they fill. On level 4, you have 4s, 4p, 4d, 4f, 5s, 5p, 5d. And this keeps going, but I'm not going to go any further. We fill in this order: 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, and then we would be to 6s. Alright, so zinc has exactly 30 electrons. Here's what will happen. 1s2, 2s2, 2p6. That takes care of 10. Then 3s2, 3p6. That's another 8. We're up to 18. 4s2. That's going to be 20. And then back to 3d. After 4s is 3d. And we said we are now up to 10 plus 8 plus 2. We're up to 20 electrons. Zinc we said was number 30. So 10 more electrons. And there's our 30 electrons. And this would be our entire electron configuration for zinc. If we were going to draw out the orbital diagram, it would take more space, but we could also do that. 1s would have 2 electrons. 2s, 2 electrons. 2p, 6 electrons. 3s, 2 electrons. 3p, another 6. 4s has 2, and then 3d has 10. And this, a little sloppy, would be our orbital diagram for zinc.